Welcome to System 2.
Today, we are diving deep into a puzzle that sits right at the heart of our modern world. We're calling it the energy paradox.
And let's just start with a really big question. Think about this for a second. The very engine that built our entire world, the source of our light, our heat, all of our incredible progress, what if that engine is now threatening to just break it all?
For the last 2 centuries, our civilization has been absolutely hooked on one thing: fossil fuels. And it makes sense, right? They're incredibly powerful, they were cheap, and they fueled, well, everything. From the very first factories to the phone that's probably in your pocket right now. But all that power came with a price tag we're only now really starting to understand.
And here's the first number on that bill. The Intergovernmental Panel on Climate Change, the IPCC, they've shown that the planet has already warmed by 1.1 degrees Celsius. That's not a projection. That's the direct cost of our fossil fuel age, measured on a global thermometer. And let's be super clear about this. The science isn't fuzzy. It's overwhelming. The IPCC's own words are that this warming is, and I quote, unequivocally caused by human activities. So, yeah. There's really no room for debate there.
So where's all this stuff coming from? Well, this chart breaks it all down. And what's fascinating is that the energy sector is the biggest piece of the pie by far. We're talking more than a third of all global greenhouse gas emissions. It's the engine room of our global economy, for sure, but it's also the main source of the problem.
But, just as the problem became impossible to ignore, a really powerful solution started to emerge. And it sparked nothing short of a full-blown renewable revolution.
And this right here shows you why. Just look at this cost collapse. In just 9 years, the cost of solar energy absolutely plummeted by 85%. Wind power dropped by more than half. And the batteries we need to store all that juice also down 85%. This isn't just some gradual shift. It's a technological earthquake.
And this is the crucial takeaway, the thing that changes everything. We've hit an economic tipping point. In a lot of places around the world, building a brand new solar or wind farm is now actually cheaper than just continuing to run an old coal or gas plant. So clean energy isn't just the green choice anymore, it's very often the smartest economic one, period.
And because of that new economic reality, we're seeing this massive boom in clean energy. The growth is just explosive. And get this, the International Energy Agency says China alone is on track to build more than half of all the world's new renewable capacity by 2030. The sheer scale of what's happening is, well, it's staggering.
Okay, so with costs in the basement and deployment going through the roof, this whole transition to a clean energy future seems kind of inevitable, right? It's just a simple case of swapping out the old, dirty engine for a new, clean one, isn't it?
Well, not so fast. Here's our reality check. The journey, it turns out, is not quite that simple. We're starting to hit some very real and in some cases pretty hidden hurdles.
So let's go back to our engine analogy for a second. What if that shiny new clean engine requires all these specialized parts that are incredibly rare, or parts that we just can't dig out of the ground fast enough?
And that brings us to the great paradox of this whole green transition. See, on one side, you have this massive ambition, our global goals for a huge build-out of solar and wind. But on the other side, you have a very real, very physical bottleneck, the critical minerals that we need to actually build them.
And we're talking about specific stuff here. If you want to scale up solar power, you're going to need enormous amounts of silver, copper, and indium. For those giant wind turbines, you're looking at tin, zinc, and a whole lot more copper. Now, these aren't necessarily the rarest metals on Earth, but the sheer volume we're going to need to build a whole new energy system, well, that's creating a massive global supply chain headache.
But the hurdles, they're not just in the ground. They're in the air, too. Our electricity grids, the poles and wires that get the power to us, they were designed for a totally different century. A lot of them just can't handle the flood of new renewable energy. And this leads to a problem called curtailment, which is basically a fancy word for something that is just wild. Grid operators are literally forced to turn off brand new wind and solar farms, just wasting perfectly good clean energy because there's nowhere for it to go.
So all these physical hurdles, from minerals to grids, they're forcing us to look at this problem from a totally new angle. Maybe we're so focused on where our energy comes from that we've forgotten to ask a much more basic question. What is energy actually for?
Now, to answer that, we need to get our heads around a concept called energy return on investment, or EROI. All it means, really, is how much energy you get out for every unit of energy you have to put in to get it. Simple enough. The higher the ratio, the better. But here's the twist. It turns out not all energy is equal. There's a huge difference between what they call final energy, that's the electricity or the gasoline you actually buy, and useful energy, which is what you actually get after it's converted into light from a bulb or motion in a car. And you'd be surprised how much energy gets lost in that conversion.
Okay, and this is where it gets really fascinating. Look at the EROI for fossil fuels. At the final stage, what we buy at the pump or from the utility, it's a pretty respectable 8.5 to 1. But when you measure the useful energy we actually get out of it, it absolutely plummets to just 3.5 to 1. More than half the energy is just lost, mostly as waste heat from things like, really inefficient car engines.
So what's the magic number for renewables to compete? It's this, 4.6 to 1. Because electric systems are just so much more efficient, they only need a final EROI of 4.6 to deliver the exact same amount of useful work as fossil fuels do with an 8.5. And here's the kicker. Most new solar and wind projects are already well above that number. This one insight, it completely changes the game.
So, all this brings us to what is really our generational challenge. The path forward isn't some straight line. It's a complex, kind of paradoxical journey we're all on.
I think maybe the best way to think about it is with this metaphor. The transition isn't a simple swap. It's like trying to swap the engine of a plane while it's in mid-flight. The stakes are just incredibly high, and the task is, it's breathtakingly complex. So when you boil it all down, the real challenge isn't just about swapping one energy source for another. It's about fundamentally rethinking our whole relationship with energy itself and deciding together what kind of world we truly want to power.